afternoon, everyone. So today we have another historical figure, and this is a big one. This is Don Knuth, K-N-U-T-H. He is the father of algorithmic analysis. So all that frustrating big O stuff that you've had to deal with, you can blame some of that to him, because at least he had the notion of starting to compare algorithms' complexity in order to design the best possible algorithms. He also worked for the National Security Agency, the NSA, which collects vast amounts of data and tries to analyze the text in that data and potentially to decrypt it if it's encrypted. So he worked for them as a cryptographer, and that is also the area in which I trained. So I trained as a cryptographer, but my relationship with the NSA is not quite the same as his was. So Don Knuth was born in 1938, and there are a few fun quirks about him. So despite being a prominent computer scientist and being very proficient with computers, very, very proficient, he doesn't use email. And so he's quite famous that he has an assistant or a secretary. His secretary prints out his emails and brings them to his desk. And part of the idea of this is to avoid the distractions and time suck that modern email is. So if you get that famous, if you get that good at what you can do, you can avoid your email inbox. Things we can all only aspire to. He also is, of course, the winner of a Turing Award. And one other thing that he's famous for doing aside from algorithms is, how many of you have used LaTeX before? Seen LaTeX, heard LaTeX? Have you seen those nicely formatted documents you get from your math lecturers? Those are all typeset, as in there, you convert the text into a document in a language called LaTeX. And he is the creator of the TeX typesetting system, which is the precursor to LaTeX, which is the more modern version. So thanks to him, we have pretty documents. I do all my CV and all that kind of thing in LaTeX every time I have to write something that looks good. And I would hope that over the course of your degrees, if you start to do more technical stuff, that you two learn the LaTeX typesetting system so you can produce beautiful documents and send him wonderfully formatted emails that he won't read. One other thing is Knuth has a series of very well-known books, and if you can find a mistake in one of his books, you can write to him, and he will give you 256 cents in reward money. These were originally, you could actually cash these checks, but people started to forge them or sell them online for very large amounts of money because it was considered to be quite a mark of one's own accomplishment if one had a Knuth check from finding an error in one of his books. So I would encourage you to go check out these books in the library sometime, see if you can find a mistake. I'm sure there are still one or two left in there. And if you can, write to the man to get one of these checks. And I would love to see one. I've never seen one in real life. So today we have, moving on from Donald Knuth, we have a few new things that we want to start thinking about. So I've got some basic abstract data structures. We've got some concrete ways to implement them. We talked about linked lists. We talked about two different ways, in fact, to implement linked lists. But linked lists are a little easy for you guys. I know all of you have been doing pretty well. So we need to move to something just that one step more sophisticated. And to do that, I'm going to introduce you to a friend of mine. He's a very old friend. I think we look a little similar. I visit him many times a year. But he has a very large family. And he wants to know which of his descendants lived to age 13. He's got too many kids, too many grandkids, too many great-grandkids. And he just wants to know the simple answer to the question. These monkeys don't always live as long as humans, and he wants to know which one lived until 13. So being a good code monkey, he went to his computer and coded up something in C. So he made me this structure over here with all of his descendants and all of their ages. So we have Naruto, Rafiki, Sun Wukong, Abu, King Kong, King Louie, Mojo Jojo, Kala, and Donkey Kong. All are in our descendants tree. So let's try and help answer my friend the ape's question. Michael, you're up today. And we can do it from here, assuming that Rithik can manage it. You're all good? Okay. So you're helping, yeah, it's on. You're helping out my friend over here, and he wants to find which of his descendants lived till age 13. So what would be your strategy?
Go to every descendant and just just check their age. If it's like more than 13,
And
then if yes, then it's one with.
so you said we should go through each one of them one by one. So do that step by step for me.
Okay, for Naruto, then it's not. Then practically 58, then yes.
Well, we want to know which live till exactly 13, let's say.
Exactly.
Yeah.
So not practically is not. Sugmukot not. I will not. King Kong not. King Louis 13, yes. Yes.
Okay, so we found it. How long would that take in worst case, in big O notation?
And
Yeah, so if we have n items, we'd expect that to take big O of n. We have to look through, in the worst case, every item in the list to find the one that we're looking for because maybe 13 is at the bottom. Do we have a way of doing better than that for searching through something?
I think shorted and use binary search.
So binary search was our technique. So, but what did we have to do for binary search to work? Yeah, we had to sort the array. So I'm going to leave you with the microphone there for a minute, but we can definitely do better than just n. Log n was if we had it sorted, but then we have to pay the n log n cost to sort it in the first place. So there are some things there that definitely aren't ideal. So if you remember, we had binary search, which was our way of dealing with this. But we don't really want to pay that n log n cost, especially if we're doing that every time a new ape is born. Going to have to resort the whole thing. That's going to start to get expensive very quickly. So let's think about what it actually means to sort. Maybe we'll get some more insight by thinking about this a little bit more carefully. So Michael, what do you think it means to sort?
To put it in order.
And how do you figure out what it means to put something in order?
And if like you have two numbers and then if one number is less than the other, that number would be in the left of that larger number.
Yeah, so we have to come up with some kind of ordering, and the way we figure out an ordering is through comparisons between elements. Now, if we're zipping up to our high mathematical land for a minute, we might have a situation in which the objects that we're trying to compare don't actually have an order that allows them to be sorted. So our friends over at Wikipedia came up with a list. Well, no, this is just from fundamental mathematics, defines a certain number of properties that you need to have if you actually want to if you want to have a set of objects that can be ordered in a total ordering where all of them make sense and they follow a structure that we could use for something like binary search. So for us, we are unfortunately not Do we have any mathematicians here today? I know we've had a couple. We've got one in the corner. Two, John, you're a math major as well. Any other maths majors? So unfortunately, we're going to Sarah. Is that a yes? Yeah, okay, so Sarah's maths as well. So we've got a few people, but for the rest of us, we can boil all of that down to just this, really. So we really want to know for every set of possible objects for these three things to be well-defined. For it to be well-defined if two things are equivalent to each other, one is larger than the other, or one is smaller than the other. But you'll remember we had some trouble with this earlier in our semester. Do you remember watching that lecture? We had something that we couldn't do this for.
I'm not sure.
Does anyone else remember? Blake?
Arrays. Arrays, you can't compare them quickly.
Well, it wasn't about comparing directly. We were talking more abstractly. There were some things that we really had it didn't make sense to compare them. Yeah, Jack.
Strings. Like the elements within strings.
So you're on the right track there, but that's getting back into C land. What were we actually trying to do when we were having that conversation? That one not on? Okay, we'll take Michael's. Sorry, Michael, you've been usurped. I'll see if I can get that one working.
Hello? Yeah, there we go. I think we were discussing comparing like two cats. Like which cat is comparing cats.
Exactly. We were talking about compare the cats. And cats don't necessarily have a total ordering because they don't inherently possess these properties. So in order for us to make sense of a sorting algorithm for cats, we would need to ensure that each of these three properties are well defined. It doesn't matter what other things we know about the cats, as long as we have an answer to each of these questions for any two cats, then we can establish a total ordering and we can do some sorting. So that now enables us to sort our array. We can now sort our apes, even though they are structs inside of an array. It's an array of structs. We can still actually sort these because we have some sense of what it means to sort them. So we can write a function to compare things that don't naturally have a sorted order by imposing an order on them by making sure that each of these three properties are obeyed. Now, you could imagine actually writing this function, but then we have the question of, well, how do we tell the computer whenever we want to sort something that this is the right function to compare any two items? Because we ideally want to just have a function sort, and it can sort strings, it can sort cats, it can sort apes, it can sort numbers. But in order to do that, we need to have some way to tell it this kind of ordering properties that we've given it, this kind of comparison property. And in fact, using all the tools we've built so far, we do have a way to do this. So let's go to the standard C library, and it has all kinds of useful things. So one would assume that it too has a sorting function. And if you assume that, you would be right. So if we go down through the manual and we look up the sort function, we eventually come across this interesting description, defining the comparison function. And this is actually what we've now, from all our different discussions about comparing things, about ordering, about sorting, where this has led. So this tells us what a sorting function for the C standard library actually looks like. And here's an example, compare doubles. So you pass in two pointers to the two different doubles, and then you check what the result is of A minus B minus A in parentheses around those two groups, and you return that result. So that'll give you a negative result if the first one is smaller than the second. It'll give you a 0 if the two elements are equivalent to each other, and it will give you a positive number if the first element is larger than the second number. Okay, so now that we've got our comparison function, we are going to need a sort function that can somehow use our comparison function intelligently, and it will use hopefully it will use the right comparison function for what we give it. Hopefully for whatever our data type is, we've created the right type of comparison function, and then we can use our sorting function and tell it what comparison function to use to sort the particular kind of data that we are giving. So now we go into one of these more advanced C features that we're actually going to need to use in order to use the comparison function. So ordinarily, when a function needs some extra information, then you're still on for this one. Ordinarily, when a function needs a piece of information in order to be able to run, what do we use? Question from the start of the semester. How does the function know what it's running on? So if I give you I say, here is an add function, add. What extra information does the function need?
Parameters.
It needs the parameters, it needs the arguments. So if we have a sort function, what's one of the parameters to the sort function going to be based on our discussion just now?
These that we need to sort.
You need the things you want to sort, and on top of that, what did we just talk about?
And the compare function.
And you need a comparison function. So one of the parameters to the function, one of the arguments to the function, actually needs to be another function. So we want to pass a function to a function to tell it how to actually do the sub-operation that it needs to do. So in order to sort, you need to know how to compare, but we want to have a generic sort algorithm. So when we call the sort algorithm, we're going to need to pass it the compare algorithm that it should use for the kind of data that we're going to do. So the way that we're going to do this in the standard library is to use a function called qsort. This is our generic sort function. And let's look at the parameters. So we have void star array star array. Let me say that again, void star array. So that is, what's that? Hold the microphone really close. You've got a quiet voice. Yeah, but more concretely, out of the different things that you were talking about that we need for the function, looking at the screen right now, what does the array contain? Yeah, those are the things we want to sort. So that's the first parameter. The next parameter is the array size. And remember, we need to pass around the size of the array you see. And then the last thing,
comparison function.
yeah. So you'll notice that this is of comparison underscore fn underscore t type. So that is a function pointer that is defined as having certain properties. And what do I mean by function pointer? It's what it sounds like. It is a pointer to a function. So if you write the name of a function in C, but don't include the arguments, what the compiler is going to give you back is it's going to give you back a pointer to where that function's code is located in the computer's memory. Because remember, when you run your program, it copies all the code for your program into the computer's memory and then starts reading it line by line. So one of those lines is your function. And so when you pass the function as an argument to another function, what it's doing is it's pointing somewhere else in the computer's memory and saying the code you're looking for is over there. If you try and run that thing, go over there and find the code. And that's actually what's going on. And we call this process polymorphism. Specifically, it relates to a function that can process multiple different kinds of data. So does anyone, I'll let you think for a few seconds, can anyone come up with an idea of where we might have a function or a machine or something like that in ordinary life that obeys polymorphism or that has polymorphic properties? Okay, then we can pass it down to Toby, if you can reach. There we go.
Ordinary life.
Yeah.
Well, maybe, like the course we're learning now is kind of polymorphism. Like we're running a function of foundation of algorithm, but we're using another function called maths. Which
I think that one's a bit of a stretch. So when you are hungry and you're at the train station and the shops are closed, what are your options? Assuming that your train's coming in like 5 minutes.
not quite sure.
Not quite sure? What about this? Who's used one of these in the last year? See at least one. Oh, a couple hands. Ella confesses. What did you buy? Doritos? Jack?
Green tea.
Green tea from a vending machine. It's a cool.
Okay.
Oh, you mean like the bottled green teas? Oh, cool. And remind me your name again? Rania. What did you get? A Snickers. So these are all pretty different kinds of items. So we had a packet of chips, we had a chocolate bar, and we had a drink. And no matter which of those types of things you want to buy, the interface used to buy that kind of object is the same. So you press the buttons on the front, and it doesn't actually matter what kind of object you're operating on, the vending machine still behaves the same way. It presents you the same interface and the same kind of output location. So you don't have to go to a different location in the machine or do a different thing to the machine, depending on the type of object that you want out of it. Likewise, with the input slot for the machine. So if we're being old school, what do you put into a vending machine? Coins, right? And coins are in all different sizes, but the machine doesn't actually care. As long as it's a valid coin, doesn't actually care what type of coin it is. It can be a big coin, it can be a small denomination coin. They're all different sizes, and yet the interface that it presents to you is the same. So this is the same kind of idea as qsort. Qsort had a single interface no matter what kind of object we wanted to sort. The only thing is we had to give it an extra piece of information that was the comparison function, because it doesn't have built-in knowledge of all the different possible types. So where is this comparison function located? Well, let's go back to our memory diagram from earlier in semester. We now know all about the stack, which is where our normal variables are. We know about the heap, which is all our malloc variables are. And now let's go all the way down to the bottom. We have our text segment. This is where the code for the program is stored when you start running your program. So in your computer's memory, let's imagine this big chunk. As soon as you start the program, it allocates space for the main function in the stack, which you've called malloc. It puts things in the heap. But what about the code for the main function? Where does the computer read the next thing that it should do? That's stored in the text section. So if I'm going to run a tool for you in a second and compile something, we can actually see some of the stuff that would be, some of the bytes that would be present in the code section. So let's do that now. And I am going to, let's see, what is this function? I don't know what this function is. Okay, that's some linked list function. It doesn't really matter, program. Doesn't really matter what it is, but I'm going to use this tool called obj dump. It doesn't matter if you never use this again, but essentially this just allows me to see the actual bytes that the compiler has produced and look at them in a reasonable way. So I'm going to do obj dump on this file. It's just a program I made earlier. And if I scroll up a whole lot, disassembly of section text. And here is the pop function from my linked list implementation. And it will tell me, well, at this address, there is a byte whose value is 55. At that address, there is a byte whose value is 48, then one that's 89, and then one that's E5. And so that's on the left side over there. And on the right side, it's telling us what they're equivalent to in the computer's underlying assembly language. So remember, this is an interpretation of the bytes into some kind of code that the machine will actually run. So if I then scroll down, I can see the main function similarly has some bytes, and all our functions seem to start with the same little bit of code. And what this bit of code is actually doing is it's setting up the stack for the new function. Because remember, when we add a new stack, that gets added, a whole new frame gets added to the stack with its own new variables. And these few bytes that we see at the start of every function are those instructions that help the computer set up that new stack frame. And if we look just a tiny bit more into it, remember we've already talked a little about stacks where you can push something onto the stack on the top and you can pop something off the top of the stack. So what are the assembly instructions that we use to do that? Well, this is showing us we're pushing a new stack frame onto the top. And let's look at the end of this main function where it ends and see what the instructions are there. At the end of the main function, we have a pop as well. So this is giving us a sense that what we're doing to set up the new stack frame is we're pushing some new things on, and at the end, we're popping them off. So this is some details that you'll learn if you do more advanced systems level classes that actually have you understand at the lowest level how the computer is actually dealing with all these things. So that's our brief interlude into how function pointers work. But now we actually care about using them. So all well and good that we understand it. What do I actually have to do practically? So here are my secret 3 steps to creating a function pointer. Whoa. Here are my secret 3 steps to writing a function pointer. So the first thing to do, just write out the function prototype normally. Then put 2 parentheses and a star around what you've just done, around the name of it, and then prop it. That's it. So let's take a look at a qsort example that I prepared earlier that will illustrate to us how we can actually do this. Okay, so this whole file is dedicated to just running some quicksort on a bunch of strings. This is an implementation of ternary quicksort, which we discussed a little bit earlier in the context of doing faster string sorting algorithms. So this is an implementation that I cooked up. It's a little bit complicated, but our main thing that we're going to care about is the usage of qsort in here. So the first thing, remember, if I want to use qsort, then I need this comparison function that I've been talking so much about. So what I've done is I've written a function called myStringCompare, and this is essentially just a function that compares strings. You could probably write a version of this yourself without too much difficulty. So what it does is it first checks to see if there is another spot available in my string. It first checks to see if this is pointing to null, because if it's pointing to a 0 byte or a null character, then I shouldn't move on and keep comparing. But if it's not, it checks to see if the pointers pointing to the current location in the two strings are equivalent. If it is, it says that it's done another successful comparison. And so this is just for the first one, and then I'm essentially repeating that in a loop. So this is making sure that the string actually does have that first character. And then just like our double compare function before, we are doing S1 minus S2. But here what's actually happening is we're looking at how far along in each string we've gone. So we're making sure that, so what it's actually doing is it's doing a character comparison of that particular position in the string. So that's all fine. So remember, we wanted to do lexicographic sorting for our string sorting, for our ternary quicksort. And so what this is actually doing is it is checking first to see up till what point are the strings identical. And then at the first point at which they're non-identical, it says which string has the higher letter. So that's what's happening there. Sorry for the slight confusion. It's a bit of a tricky code that I probably should have commented a little better. So we dereference the character that we're up to in S1, we dereference the character that we're up to in S2, and we compare them. So that is my string compare function. And now let's go all the way to, so there's a normal looking kind of quicksort. But let's, instead of using quicksort, let's use the built-in qsort that's built into the C standard library. So what do we need for this? Zin told us we needed a copy of the data that we want to sort. We needed a parameter that was the number of elements we wanted to sort. We needed the size of the individual elements. And what I've done here is, because each of the things that I'm comparing is a string, really what I'm doing, I have access in my array to string pointers. And so the size that I'm giving here is actually the size of a string pointer. So that's kind of tricky, and something you have to watch out for when you're using qsort is to be sure, are you comparing pointers to things and using a fancy way to dereference the pointers, or are you comparing the objects themselves? So there's a difference between comparing structs and comparing pointers to structs, but using a comparison function to dereference those pointers. And then here, I just have the name of the function that I'm using. So I didn't even need to use my complicated syntax. I could just pass the name directly, because when I declared my compare string up here, I've already actually created it in memory somewhere. So I didn't need to use the special syntax for declaring a function pointer on its own. Another thing to note is that C will automatically dereference a function pointer as soon as you try to call it as if it was a normal function. So if you use the syntax, the function pointer, open parentheses, all the arguments you need, close parentheses, you don't have to worry about the fact that it's actually a function pointer rather than just a function. C automatically deals with that for you.
So this is not the actual point of a function pointer. And what's the use of it?
So we just saw that that's the only way that we can do polymorphism, for example, in the qsort function. In order to give it the code that it needed to do the comparison on cats, or to do comparisons on ape structs, or comparisons on something else that isn't a built-in type in C, we need to give it the instructions for how to do that comparison. And the way you give it instructions is through a function pointer.
The only use of function pointer, or is this the only use we need for it now?
There are other uses. So for example, if you want to build up more layers of abstraction, is why you might use a function pointer. So say you want to give the struct the ability to contain a bunch of functions that allow you to operate on the struct. So every time you pass around the struct already contains within it some built-in functions. So rather than having, let's say you have what's a good example? You have two different vehicles. You have a car vehicle and a rocket ship vehicle. And you want to have a function called compute coordinates. Now, one way to do it would be in your compute coordinates function to check if your if the struct you're passing in is of type car or is of type rocket ship. And then you need to have a field in those structs saying what kind of vehicle it is. That's one way of doing it. Another way of doing it is to have inside the struct, you could have a function that's called calculate trajectory. And so then what you do is when you get that, whenever you're handed the struct, you can always use the calculate trajectory with the given time up there. You want to figure out its new position. And so that allows you to hide some of the details and to not worry about them in terms of creating this one really complicated function, but you can instead package things up neatly. And that can make your code a lot simpler. At the end of the day, all of these techniques are not strictly necessary. It's not even necessary to have functions. You can write code with no functions at all and just tell the computer to jump higher up into the code that you've already written. C does have a way of doing that. But that makes your life miserable as a programmer. So part of this is about designing abstractions that allow us to think about our problems in ways that are conducive to actually writing algorithms that solve the problems. You can make linked lists without structures as well, just using raw pointers, but that'll get nasty really, really fast. So that's why we introduced these tools. Okay, let's see if there we go. So we've now got a few more examples of a function pointer. This is what we'll actually use. I'll cut the earlier bit out of the demo because that didn't work. So here we have a simple function f, and it's of, that's what I was missing. I was missing the return type before. Okay, start again. So the things you need the full prototype for the function, including the return type and the arguments. So let's write that out as if it was just the normal function. So there's our normal function f. It takes in one double and returns a double. Ooh. And to turn it into a function pointer, we add the star and the parentheses around the name. So now we have a function pointer for a function that takes in a double and returns a double. And we have a variable, I think that was meant to be a double as well. X is 2.0. So now let's set f to be the square root function. And you'll notice here, I'm just using square root. I'm not adding brackets. And I'm not adding brackets because as soon as we add brackets, the computer, instead of using it as a function pointer, will dereference it and immediately run it. And we don't want to calculate the square root of x. We just want to set the function pointer so that if we want to use f somewhere, when we run f, it'll refer to the square root function elsewhere. So now what we can do is we can just call print, and we can use f as if it was the square root function. Now we can reassign f, and now f is the sign function. And so if we run the exact same print line we did before, now f will be sign, and it'll compute sine of x instead of the square root of x. Now one last time we can do it with log as well. So let me get into the place where I stored that.
Go hanging bracket.
There we go. Thanks. Which directory was this in? This was in vector 9. There we go. Vector 9, code, and then clang. There we go. And should be no surprise to all of you that when I run funcPoint, even though I'm running it on the value x equals 2 each time, the first time f of x gives me the square root of 2, which is roughly 1.41. The second time I do it, it's giving me the sign, and then it's giving me the log. We can see we used the function pointer successfully. The other thing to note is over here, this other syntax. So what I've done in this other syntax is I've explicitly dereferenced the function pointer and then used the argument. But you can see that's got an awful lot of parentheses and gets a little confusing. And that's why C automatically dereferences the function pointer. And where's the microphone? Toby, do you want to pass it back? Maybe don't throw it. That might end badly for the microphone. You'll have to remind me your name again. Sujay.
Is there a question at the top?
Is that on?
So you know at the top you said that you shouldn't be using like you have to put the star like at the very top on line
Yep.
number 9, I think.
So I'll scroll up for you.
Yeah, when you're defining the function pointer, right? You said that you need to put the wait, no. Sorry. I sort of so when you like line 11, sorry, in where f is equal to the square root function or something like that, and you said at that time C automatically like dereferences functions if you put them with parentheses and with like a parameter.
Once you've declared it.
Yeah, once you've declared it. So in line 11, if you were to put like the ampersand in front of the square root, would you like, and then you put like parameters and stuff, would it still give you the function pointer? Or would like the same way how you use ampersand and get the address?
That's going to come down to order of operations. We can try it and see what happens. It won't work, but how it won't work, I'm not sure. Okay, it says that's against the rules of the C language is essentially what it's saying there. And the reason why it's against the language is precisely because it introduces this ambiguity.
Okay, because you know.
But that was an excellent question. Other questions before we move to the next code demo? Finn, let's somehow get you a microphone. I'll give you this microphone while we pass that one back down to the front. It was Sujay. And there we go. Right, no link, no link. On.
I was just wondering what the type of F is because it's hard to read it on that line 9. Like what exactly? It looks like it's a double, but I know it's not a double. How is that read exactly?
It is a function pointer that takes in a double to a double and returns a double. So that is its type. So it's a pointer to a function, and the type of function that it points to is a function that receives, that takes as input a double, and then outputs a double.
So if you see something, I guess, formatted like that, that's just read as you just said.
Yeah. There is a website online that if there's like some awfully complicated type declaration that you can like put it in and it gives it back to you in plain English. But I don't remember the website for that. I've had to use it a few times in my career where the type declaration is too complicated to read.
Okay, thanks.
No worries. Ella, is that a confusion face or a deep in thought face?
It's so when you say declaring a function pointer, is that always done within the function? It's not an argument that's passed, say, through main.
It could be both.
Okay.
So remember qsort, we had one of its parameters was a function pointer.
Yeah.
And the reason why it was a comparison pointer underscore t is because if you were to write this kind of syntax in the function prototype, it would look really confusing. And so what someone has done is they've type defed that function pointer type so that you can use it as a parameter without having to have all this strange stuff.
Okay, that makes sense. Thank you.
Anything else?
That's okay.
Okay. Anyone else with questions? Yeah, Rex. I think this is the first time I've successfully said your name in class.
When you did the prototype, you said that the parameter takes double.
Yeah.
But you didn't give it a name. Normally, when we use prototypes, we would give it a name because we know what the name of that parameter is going to be. But every time we make a prototype, is that just by convention and give it a name, or does it work? Don't give it a name, just say that it takes a double.
I don't think it would work if you didn't give it a name. I mean, in theory, I could imagine a way in which you could build a program that would still work like that based off stack locations. But the reason we can do it here, ignore that first part of the answer. I think it's correct. But the reason why we don't need it here is because we don't actually have the code that's associated with it. So even if we gave that variable a name, there wouldn't be anything to do with the name because the name is only relevant once you define the function body. That makes sense? Anyone else? Sebastian.
So I don't know if this makes sense, but when we use a library, let's say we have a program and we include the math library, and at some point we use the square function. Are the functions from the library pointers? And when we use the square function at some point, we're dereferencing that pointer?
Yeah, that's what's happening behind the scenes.
Oh, cool.
So behind the scenes, whenever you make a function, what you've done is you've placed that somewhere in memory, and then when you use the name of the function, what the compiler does ordinarily is it will swap out the location in memory for that place where you have that function's name, and function pointers just makes that more explicit and allows you to do it when the program is running rather than just when the program is compiled. So you can imagine the compiler knows where all the functions are going to be ahead of time, so it can swap them in. But if you want to do that process manually at the time the program is running, you can still do it. Okay, more questions. Sarah.
So we've gone over before, but what are the advantages of using a pointer to a function rather than just calling the function in the program?
So there were a few of them. I think it was, what's your name again?
Alistair.
Alistair. I will get it, I think, for next time. I've asked a few too many times. So the same question as Alistair, which is essentially why bother with all of this? One of the reasons was the thing I was talking about before, where if we have like get trajectories and would use for different kinds of vehicles, and we want to have one type of struct that we pass around, and no matter what type of struct it is, we can always call get trajectory. So we can store the function within the struct, a pointer to the right function for that time. So let me sketch that out for you, and then I'll answer your question a bit more as well. Alistair, is that a follow-up from this? Okay, you can ask it as well, and then I'll do the little explainer with the code.
Oh, so yeah. I understand the part where you can, like, you're storing the function in the struct. So do you have to put the same inputs you would normally do for that function? Or
Yeah.
you short?
So that's the idea of polymorphism, is both of the ones should have the same types of input and the same types of arguments so that you can use a function pointer that's consistent between them.
Straight away instead of like having to
Yeah.
initially write it. Okay.
So I think that explanation might have escaped Sarah. So we will write a little bit of code that makes this a little clearer. Now, I haven't done this live in class before, so there are likely to be some errors in what I write, and please help me catch them out. So, type def, and this is going to be, actually, first let's make a type def for our get coordinates function. So remember the way we do it, let's say the get coordinates function is going to take in its current position, the old time, and new time, and they'll all be doubles. And it's going to return the new coordinates as a struct coordinates. And this will be double x, double y, okay, so far so good. Now what we want to do is we want to have a struct that is a car. And a car will have, it'll have a coordinates t, and we'll call that current position. And, okay. And we'll also have a rocket. Now, right now, this is totally uninteresting, but we know that the coordinates for a rocket and coordinates for a car are going to evolve according to different equations. Let's imagine that it's rather than a powered rocket, it's a rocket that's like following a ballistic trajectory. So we know that there are normal physics equations of motions that would follow that we could put into the get coordinates function. So now what we could do is we could write our function let's add So now let's make our get coordinates function. So let's first write out what it would look like just on its own. So the get coordinates function will return a new coordinates object. And what it'll have here is it'll have the old coordinates, and then if we want to do this for a car, we could write one function. So I could go ahead and write in the an equation that's for 2 dimensions for when a car is driving down the road, acceleration, velocity, blah, 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 blah. And then every time I pass around a car, in order to update its coordinates, I could call get new coordinates car. I could also do this for a rocket, and it would be a different function, right? And I could, depending on what it was that I was operating on, I could call the different function. What function pointers allow me to do is I can have one function type called get new coordinates. And let's now turn this into a function pointer, because the way I do that is just the steps I did before. And now I have the type signature for a get new coordinates function. So now I can store this inside my rocket, and I can also have one inside my car. Or even better, let's just do vehicle. Let's call this a vehicle. And now what I'll do is I'll have a new integer, which is type. And type, if type is 0, let's say it's car. And if type is 1, it's a rocket. And now I can write my new functions, coordinates t. If I do new car, and this is going to return a vehicle t type. Return a pointer to a vehicle t. So vehicle p pointer v equals malloc size of, this is really getting to be an extended example. Okay, so we malloc a new vehicle. We set its type to 0 because 0 is type car. And then what we need to do, and this is really the critical thing, is get new coordinates will be a function that we'll write called get new car coordinates. And then v dot. And so this allows us to hide some of the implementation details behind extra layers of abstraction. So we could have in another file, it does everything for cars. In another file, it does everything for rockets. And we don't have to worry about it. All we need to do, if we're the programmer, we just use the vehicle the same way, no matter what kind of vehicle it is, trusting that the code we've written somewhere else, and our function pointer will make sure that when the functions for that actually runs, that it's relevant to the type that we're doing it on. Does that help a little bit? Yes, okay. Some success. Other questions? No more? We're okay with function pointers for now? Surya. It wasn't Surya, it's Sujay.
Wait, like, is the thing about the size of the function pointer, is it always the same, or does it change depending on the function?
On the same computer, a function pointer is just going to be the size of an address. Because what a function pointer is just like any other pointer. It tells you, it contains the information about where in memory something is. And for a given computer, the amount of memory you need to know to figure out a location is the same. Maybe, Toby, you can keep that for the minute, just in case we need to pass it back somewhere there. Okay, that was quite a long demo, and we are now out of time as a result. So we are going to continue on with some of this discussion next lecture, and then eventually get back to tying this back to our whole ape discussion of how to figure out the oldest ape in a series of generations using this kind of technique. Thank you very much, and I'll see you all next week.